You see my full screen now with my slide, yes?
Yes, perfect. Thank you.
And do you see my mouse when I do this?
We see your mouse, yes.
Thank you. Yeah, perfect. Then I will start. In this first part of the webinar is supposed to be 30 minutes. And Konstantin, I have some time here, but if you can just give me a little bit of a cue by the end, that will be great. So as Konstantin already introduced, I'll be talking today about vibrational spectroscopy and FHI-aims. Actually, vibrational spectroscopy is what I'll focus on the second part of my talk. The first part will be basically an introduction to what FHI-aims is, what is the code, what is the underlying framework with which we can perform this type of vibrational spectroscopy simulations. And that part will have a little bit of an overlap with previous webinars just to set the stage. And then we'll move into the vibrational spectroscopy piece that is a little bit more focused on what I'll show today. And then on the second talk is Alex talking a bit more about a scientific case of the solid electrolytes. So yes, as Konstantin mentioned, I'm in Hamburg, Germany, and my name is Mariana Rossi. In case you do not know me and we have never met before, this is a photo of myself with my group at the end, at fall, beginning of fall last year. And we're an independent research group hosted at the Max Planck Institute for the Structure and Dynamics of Matter, as I mentioned, in Hamburg. And the group is called Simulations from Ab Initio Approaches, but it has this nice acronym that Konstantin mentioned, which is SABIA, which is a bird from the country I am from, where I grew up in and where I studied most of my life until I moved to do my PhD abroad. So that's us there. And in this group, myself and many of the members, we contribute to and co-develop the FHI-aims code. And I am also one of the coordinators of the code. So moving on to talking about FHI-aims itself. So FHI-aims is a code that started around 20 years ago in the Fritz Haber Institute in Berlin. And the code was developed with this vision that is written here, that we wanted an electronic structure code that could really treat realistic and complex molecules and materials and give a prediction of their properties from the point of view of electronic structure without sacrificing accuracy even when you go to large sizes, right? And so the framework that we have today is something that achieves an all-electron implementation of electronic structure problem in terms of the Kohn-Sham DFT mostly, but I'll talk more about that later. It can treat both non-periodic and periodic systems on equal footing, so you can really go through both types of simulations in the exact same code. It achieves a really great scalability up to large system sizes. We can do many thousands of atoms. You will see actual examples in my talk about that. And we don't have to sacrifice accuracy or precision. And the current version of the code really achieves this scalability that I can do, simulations on my laptop or, on massively parallel high-performance computing architectures. And it works in both cases, of course, depending on the size of your problem that you want to solve. But it really scales very well and is also cheap enough to do in your computer, in your own laptop if you need. And of course, one of the nice things is also that even though, let's say, I would say at least that the workhorse of the code is really ground state density functional theory, it also has a huge support on explicitly correlated methods and very advanced implementations of random phase approximation, GW, and couple cluster via some interfaces, for example, to CC4S and other explicitly correlated methodologies as well. So all of these all these bullet points that I have read through and mentioned now are really possible because in the code there is this critical choice that was made that the basis set are numeric atom-centered basis functions. Yeah, and this is really critical to achieve this efficient all-electron implementation, to achieve scalability and many other properties that I'll go a little bit more inside into soon. The last thing I want to mention here on this slide is that nowadays the stewardship of the code is basically hosted in this non-profit organization called Molecular Simulations from First Principles. The purpose of the organization is to support basic science, and we support the code. The advisory board of the organization is made by myself, Matthias Schäffler, and Volker Blum. Volker Blum is also the person that did the slide originally that I am showing you today. And he's also the person that wrote the first line of this code almost 20 years ago. He continues to be doing a lot for the implementations and the coordination of the code, of course. And of course, it's not only us. Actually, the code is really, the development of the code is based on a large and very active community. So it's a community-based code that gets a lot of scientists contributing to this. Yes, so going a little bit more into the critical choice of the numeric atom-centered functions, this is how it looks like, and you know, this is something special of FHI-aims, let's say, that this formula you see here on the other screen. This formula that you see here on the left, it's usual. Many of you have seen this before. So psi k of r here represents, for example, a single particle Kohn-Sham orbital, and you do a linear expansion of this Kohn-Sham orbital into some linear combination, right, of atomic orbitals. In this case, it's basis functions here, phi I of r. And these are the basis functions that are numeric atom-centered orbitals that we use in the code. So they're atom-centered, as the name says. So each atom in the system will have its own set of basis functions. The basis functions are given here by the expression that you see in red. So it has an angular component, which is just a common spherical harmonic, YLM. And then the radial part is really the crucial part, let's say, that has a lot of flexibility. It's numerically tabulated on a dense logarithmic grid in the code, and it's splined very smoothly and so on, and it can provide the necessary flexibility to describe these fast oscillations that you have close to nuclei in an all-electron framework. At the same time, because they capture this so well, you end up with a small amount of basis set that can very accurately give you, it can quickly converge the total energies and so on. So you don't need large basis sets. So the code is also efficient because of that. And also because these functions, they decay to zero here after some distance that they go away from the nuclei they are related to. We can also apply a cutoff potential that really makes them strictly zero after that cutoff, and that makes the whole framework strictly localizable. So for most integrations that we do in real space in the code, actually we can achieve this order n scaling because we are localized, because the basis sets can be localized, and so the code scales basically for all operations except the eigenvalue solver as order n. The eigenvalue solver is also not the bottleneck of most calculations unless you go to very, very large system sizes. So when you look at scalings in the code, you typically see order n for up to very large system sizes. And the nice thing is that these basis sets, they are shipped with the code. They have been optimized for all elements from, as you see in the slide, from 1 to 102 atomic number. And they deliver really accurate and precise results for a cost that is not really large. And this accuracy and precision that I'm talking about, and also the scalability, they are not just words. Of course, they have been benchmarked by ourselves and also by a larger team of colleagues in the literature. And these are some of the papers you can look up. So this is one paper from 2016, which is the famous delta test, that was comparing many different electronic structure codes in order to yield the equations of states of I think 70 elemental solids, and they conclude that all electron implementations are really the most accurate and precise, and FHI-aims came as one of the most precise codes there. Then there was this other study here, which was looking at molecules and total energies of molecules. And they look at several different types of basis sets that code uses, like Gaussian basis sets or STOs or numeric atom-centered orbitals. And they also actually see that numeric atom-centered orbitals deliver better accuracy on total energies of these hundreds of molecules that they looked at. This is another benchmark which looks at electronic band structure and spin orbit coupling correction, so how precise that can be in the code, arriving to a good result in the end. And finally, I would like to highlight also this contribution from 2023. It's a roadmap that looks at the, several different electronic structure codes and how they fit into this exascale computing era, and they represent and quote a few scaling benchmarks and so on of FHI-aims if you're curious how we have benchmarked that. So, of course, everything is a continuous work and we continue to improve all the time. So even after all of these papers, basically, we continue working. So this is an even more recent paper that I'll quote in a moment. So from the beginning of 2023 to the end of 2023 up to the middle maybe of 2024, we did a lot of improvements on the GGA functionals, as I show here, and also on the hybrid functionals implementations in the code. So what you see here are two systems that I particularly was interested in and I benchmarked. This is an ice structure with many, many molecules, 512 molecules, and this is a van der Waals heterostructure. And this is just the time per SCF iteration that we had in a 2022 version of the code in yellow and a 2023 version of the code in orange. And these are improvements that we did on the handling of the Hartree terms, so the electrostatic terms in the code. And you can see that for some systems we can get a larger speed up than others, but it's very nice. It's becoming faster every time. This was just a rewrite of how we write the routine. So it's more computer science than it's not a new algorithm, but rather restructuring the code. Much more dramatic than what happened to the GGA functionals was what happened to the hybrid functionals. So there we also looked at the implementation, the periodic implementation of hybrid functionals, and we already had an implementation in the code since 2015, basically. And this is for gallium arsenide supercells and the HSCO6 functional, which is a range-separated hybrid. This is how the dashed lines is how the code was scaling in the previous version. From green to purple, you increase the number of atoms in the system. And these lines here below, which are the full lines, is how the code is scaling nowadays. This is with number of cores, you see. And what you see is that the new implementation, which has more layers of parallelization, it parallelizes over different elements in the code, basically. So we changed all of the layout, basically, of the implementation. It achieves really almost ideal strong scaling, and the prefactor is much reduced. So we have a time to solution reduced by basically 2 orders of magnitude. And this is also reflected in the order n scaling here. So now this is how it scales with number of atoms. The original implementation was also order n scaling in that respect, but with a much larger prefactor than we have now, right? So this current status of the implementation really allows us to do very large simulations with hybrid functionals, or do very fast and very efficiently simulations for smaller system sizes. This and also these improvements in the electrostatic potential and so on, they are all summarized in this publication, the JCP from last year. The 2 first authors here, Sebastian and Florian Merz, are the ones that are responsible for all the incredible wonders that were really achieved. They coded most of the things, and the rest of the authors, we were talking a lot and we helped, but I feel that they really deserve a lot of credit for this. And so what we show there is that now we can achieve simulations. You see, this is a plot of the paper. If you're interested, you can look at more details there. that we show calculations with hybrid functionals for systems containing up to 30,000 atoms in the time per SCF step that really is okay for this type of system, right? So it's a very, very fast, very, very efficient, and it's amazing what we can do now with that. So that's not all. Like, we also have a very, very advanced implementations of dispersion corrections in the code. And this is something that the next speaker, Alex Tkachenko, is the person that drove the first implementations for sure. So this is the 2009 paper from Alex and Matthias Scheffler, where they proposed the pairwise van der Waals correction that was first implemented in FHI-aims, and of course it's still available there. It's a very successful correction. After that, there was also the many-body dispersion correction, which is also available in the code. And even more recently, this many-body dispersion NL that extends a bit this many-body dispersion framework for systems that are highly polarizable and so on, so it can treat more effectively metals and for example, two-dimensional materials like TMGCs and so on with this approach. It's also available in the code and with a very nice implementation through this libmvd that Alex also supports in his group. And then we also have now some other, let's say, van der Waals corrections from other families of van der Waals corrections. So the XDM by Erin Johnson and Axel Becky. This is the exchange dipole moment corrected hybrid type of van der Waals correction. It has forces and everything in the code, so it was a very nice implementation that you can also use. And more recently, even Grimme D3 correction has been put into the code. So the nice thing is that you can look at all these different types of corrections within the same framework and see how they fare for your system. Okay, so now that we have all of that and all of these tools, the question is really, can we simulate vibrational spectroscopy with FHI-aims? And this is the second part of my talk. And I would not be giving this webinar if the answer was no. So of course it's yes, that we can simulate that. But I'll try to tell you a little bit how we can get the ingredients to do these simulations and which types of functionalities of the codes you have to use in order to do that. And then more hands-on, you'll see in the tutorials how to actually do it. So if you want to actually hands-on do it, this will be in the tutorials. I'll show you here a bit what you need and how it's implemented and so on. So vibrational spectroscopy, maybe as many of you that are here today know, is a very important technique to be able to experimentally realize or simulate, because it gets the material to tell you something about its nuclear motion and the allowed vibrational transitions, which in turn can give you a lot of information about what is the structure of the material, what is the chemical composition of the material. It can probe what types of bonds you have in your systems. It can probe the potential energy surface and much more. And so, of course, there's a huge interest in simulating that, and also a huge interest in being able to simulate something that you can directly compare to an experimental signal, right? So there are many, many different types of vibrational spectroscopy techniques, including linear and non-linear ones, enhanced, plasmonically enhanced ones, resonant or non-resonant ones, and so on. So the zoo is very, very large. And for each one, you need a different kind of ingredient, let's say, in order to be able to simulate that spectrum. There's a lot of theory that goes behind getting these expressions that you need to calculate in order to simulate the spectroscopy that you want to compare to. But the most widely used, or the ones that are most common to see, is infrared absorption and Raman scattering, right? So these are the most common ones, and they are types of linear spectroscopy, okay? So I show here in the table, like this is work after you figure out what type of spectroscopy that you're doing, and then you figure out what is the cross-section, either the cross-section of absorption, so what is the probability of absorption of your system, this is in IR, or the cross-section for scattering, that's what you need in Raman. And I show you here two ways of calculating each one of the spectroscopy. On the first row here is the double harmonic approximation that is called. So that these are the expressions that you see here on the top. So the IR intensity for each normal mode, harmonic normal mode of vibration, is given by the how much the dipole will change with respect to displacements along this normal mode that I call here QI. And for the Raman case, you see that it's then how much the polarizability tensor will change along the displacement of the same normal mode. I'm writing all this expression here in simplified terms, as I put here on the bottom, because of course, this polarizability is a tensor. So, you know, like you need to see which components of the tensor you need to look at. The same thing here for the dipole. That really depends on the experimental signal you want to compare to, how you combine the different components. But the ingredients are those. And this is a harmonic approximation, or even double harmonic, how it's usually called. But the anharmonic case is also possible to be calculated. The expressions are here on the bottom. Within linear response, again, these are given by Fourier transform of some time correlation functions here, the dipole time correlation function or the polarizability time correlation function. So I put here in orange the ingredients that you need, right? So if you want to go about calculating this type of spectroscopy signals now in your system, what do you need? You need some way to calculate the dipole for either periodic or non-periodic systems. You need to be able to calculate normal modes. And the normal modes that are interesting for this kind of spectroscopy are the ones close to the gamma point of your crystal, if you have a crystal, because normally in these experiments, the wavelengths that they shoot in is such that you're only sensitive really to modes close to gamma in most of these cases. So that's the ones you want here. And here, if you want the fully enharmonic, so then you want also the polarizability in the case of Raman, these you obviously need. And if you want the enharmonic case, this time dependence here, both of the dipole and of the polarizability, they come from the time dependence of the evolution of the nuclear coordinates. So what you actually need is how to evolve your nuclear coordinates in time, and then you can calculate this type of correlation functions. So these are the ingredients. And the question is, how can you get these ingredients from FHI-aims? So you might have seen also in past webinars, I think the one from Matthias Scheffler, that there is this new code review roadmap coming out. It's currently at the draft stage, but I think now Basti and Constantine, people here can correct me, but I think that we're planning to send it out really in the next 2 weeks or so, even to archives. So if you need it sooner, you can email us, we can send you drafts. But otherwise, it should be soon, at least in archive. And in this review, you will see several contributions that I walk through here that explain to you exactly how to get each one of these ingredients that I just mentioned in order to calculate vibration spectroscopy. So the first one is, let's say you need phonons, right? You need this, if you want to calculate this in the harmonic approximation, you need phonons and vibrations for your systems. And this is covered here by this contribution, which has number 6.1, that was led by Christian and Matthias, and Tom Purcell as well. And I would like to say a couple of things about how to calculate this in FHI-aims. So for us in the code right now, we recommend you to do finite difference algorithms for phonons instead of density function perturbation theory, because the density function perturbation theory implementation in the code at the moment for nuclear displacement, right, the ones that could give you the dynamical matrix, the Hessian, and so on, has limited support. I will come back to that in the later slide in my talk, while finite differences actually are not that much more costly for system sizes that are typically the ones that you need. And it will be accurate for any functional that you use and so on. So you always get the good answer, right? So that's what we recommend, to use this. And these finite difference algorithms can be done with FHI-aims very simply, for example, by interfacing with FHI vibes, which bridges to PhonoPy. And this is a very tight connection to FHI-aims. So it's built for FHI-aims, and it's very easy to do phonon calculations with this code. You can also use PhonoPy itself directly with FHI-aims if you wish to do so. It has an interface. You can do it also through ASE. which also has an interface to FHI-aims as a calculator, as many of you might know, and this is also possible. The IPy code can also do that interfaces through the sockets or in-house scripts that you will see one example in the tutorial that can really get you the whole infrared and Raman intensities by an in-house script that connects everything. That we'll see in the tutorial tomorrow, right? On the other hand, if you want to do the enharmonic case, then you need to really get the nuclei to move. This you do through molecular dynamics. And the molecular dynamics in FHI-aims is also covered by another contribution in this roadmap. This one here, 6.2. And there are several ways as well to perform molecular dynamics with FHI-aims. There's a native implementation, which is quite robust, but has limited features in the sense that, for example, there is no barostats implemented, so you cannot do constant pressure simulations, and it's a bit limited in terms of which integrators you can use or which type of things you can do. So, but it's very robust. If what you need is represented there, then you can of course use that. FHI-vibes bridges to ASC, so it actually uses the ASC molecular dynamics module to do also molecular dynamics with FHI-aims, so you can also do that. ASC itself, of course. And IPy, which is my personal favorite because I also develop IPy, but that's another story. But in IPy, you can do, if you need to do very advanced types of molecular dynamics, including maybe nuclear quantum effects and so on, that's the code to go. It has very advanced techniques implemented in there, and it can give you lots of features there. And all of these work through socket interfaces, so it's quite efficient as well to do it with FHI-aims. You don't lose any efficiency in this case.
5 minutes, roughly.
Yeah. But then that's not all. So you have, you need dipoles, also not only for clusters, but also for periodic systems. For clusters, it's quite straightforward to calculate. To just calculate the integral of the density times the spatial coordinate over all space. And this is, it's in the manual, you can really see that. But for periodic systems, this is more complicated because the dipole is related to the polarization, which is really defined as a geometric phase of the wave function through the modern theory of polarization. So you really need that to have boundary insensitive results for the dipoles of solids, of really periodic solids. And this is something that has been implemented more recently in the code by Christian Carbonio. He did the implementation, and it's also summarized in this other contribution here in the roadmap. You can see in this case you need to take a bit of care because this quantity is multi-valued, so it's calculated like this with the Berry connection. This is the A here, and it comes in several branches. You need to branch match to be able to get dipole differences that you need for the dipole quite nicely. You see a bit of that, I think, in the tutorial tomorrow. And finally, the polarizabilities, which are then a response property of the electronic density. And this can be calculated by electric field perturbations on the electronic density in the framework of density functional perturbation theory for electric fields, right? And this is particularly useful, again, for periodic systems because you also need here a boundary insensitive formulation for this quantity. It's related to the polarization, of course. And this, within the framework of the FPT for electric fields, is quite nice to calculate. And we have an implementation there since 2018 by Honghui Shang that has been recast and reorganized and made more robust and more compatible with the rest of the code by Connor Box more recently, and that's also in this contribution here of the roadmap. These are also in archive. This is a figure from that contribution where you can see for the density functional perturbation theory parts of the code, what is supported, what is not supported. Connor did a really great job summarizing that. And you will see that for electric field responses, basically most things are supported and it works quite well for all systems. But for atomic displacements, that's what I mentioned in the beginning, not so much. So it's limited support. Okay. And then I'll take the last 3 minutes basically to show if you get all of this data from FHI-aims, what you can do or what you can discover with that. So in this case here, I'm showing a publication from my group from 2019, where we looked at molecular crystals. And you see here, we calculated Raman spectra for 2 polymorphs of paracetamol crystals. and this is the low frequency range. And you see that you can really differentiate these polymorphs by this low frequency range. You see here in the bottom, that's experiment. They see it's really different signal, and that is used actually to know which polymorph you have. And here, as you see, I calculated that harmonic approximation Raman or in the enharmonic approximation, and you can see that some peaks shift enharmonically, get closer to experiment, and it's really nice, and we get really good matches with the experiment. You can also do IR spectra for molecules, for example. This is something that I did also in 2019 for this porphyrin molecule. You see in green here is the infrared spectrum that was measured. In red is what you get from a harmonic approximation. It really doesn't match experiment at all. Even if you do enharmonic, but with classical nuclei in this case, it's the blue line, you don't get very good agreement. But if you include the quantum nature of the nuclei, which is something I'm not covering today, then you get really good agreement with the experiment because the hydrogens here really delocalize in this case. And this was basically, so this is 2019, this is the past, we were doing ab initio molecular dynamics. Nowadays, we machine learn everything. So of course, you can machine learn all these types of spectroscopy as well. And this is something we have been working on also since 2019 as well. So we show that we can learn polarizability tensors for crystals from FHI-aims, and then this is again the Raman spectra for paracetamol. In blue is what would be the full ab initio calculation, and in black is our predicted spectrum from this learned polarizability, so that's very good. We showed we can also learn the infrared spectrum by learning the dipoles on the first hand, and then we could look at the temperature dependence again of the IR spectrum of the same molecule I showed in the slide before. More recently, we showed we can also learn directly the electronic density response to electric fields. We have two papers, a paper that also just came out in arXiv last week, that we show how to do the full electronic density response. And with that, of course, you can again reconstruct the Raman spectrum, for example, here is of naphthalene, and it's a very good match to what would be the full calculation. And even more recently, this is something that will probably be submitted tomorrow, is a model where we learn the dipoles for periodic systems, and here is just the infrared spectrum of water under applied electric fields that we are doing in the group. So I just want to mention that all of this has been powered with data from FHI-aims, all of these results that I showed you here. So even in the machine learning era, the accuracy, in fact, of FHI-aims has always brought me a lot of joy, because then the machine learning methods can really learn without problems. Also for these, cross-sections, so the polarizability, the dipole that you need to calculate this type of vibration spectroscopies. And that's it. So thank you very much, and please ask questions.
Thank you, Mariana, for your very nice talk and introduction. So this opens up the second part of the talk, which is the Q&A session, which will be roughly 15 minutes. You can ask questions in the Q&A functionality here in the webinar. So if you click in the toolbar, you will see a Q&A option where you can ask questions directly, and these are we already have two in the chat. You can also ask on YouTube, so we already see also a question on YouTube, or on Kushare. So feel free to use all of the platforms, and we'll try to answer as much as possible. The moderation will be done by my colleague, James Green, so he will take over the Q&A, and thank you again, Mariana.
Thank you, Constantine. And yeah, as well as typing in the Q&A, if anybody wants to speak their question, then you can also raise your hand, and I think we can unmute you so you can speak directly as well. But yeah, I'll start first with the ones that have been typed in the Q&A. So I have two by David Abbasi. So the first one says, thanks, Mariana. From harmonic calculations, you get the normal modes. However, when you calculate the anharmonic spectrum, is there a way to assign what modes each peak corresponds to? Somewhere I've read one can use the piglet methods in IPI, but I'm not sure about the methodology. Do you have any experience with that?
Yes. So when you do the enharmonic calculation, it's it doesn't come directly out of the simulation what modes are what, right? There are several ways that you can post-process and analyze this kind of simulation. So if your system is not horribly enharmonic, normally if you project on the normal modes, then you can project your trajectories that you get on the normal modes of vibration, and then you can see which modes are ringing where, right? So then you get a spectrum for each projected normal mode, and then you can see what peaks are contributing to each mode. If it's more enharmonic, then the picture will become very blurry, right? Because many modes will mix and they will contribute everywhere, and what is it really any of that? Then you can do many different things. Some things that sometimes people do is to define a renormalized Hessian, so or dynamical matrix, something that is more consistent with the temperature-dependent normal mode, something like that. So there's a lot of that in the literature, and then again do the same projection. So it's kind of a renormalized harmonic basis or something like this. And then you understand things like that as well. Or you really look at motion in Cartesian space. I mean, you have to do some post-processing. That's I think my main message. And then there's, I think, an unrelated question, I think, about Piglet in IPI. Yes, you can use Piglet. So Piglet is a thermostat that uses colored noises in path integral framework in order to accelerate the convergence of path integral calculations with the number of replicas of your system or beads that you use. It's not relevant in the context of vibrational spectroscopy because this type of thermostat really messes up all the correlations in your potential energy surface. And because here, for this type of spectroscopies, you need to calculate an autocorrelation function, and it needs to be faithful to the correlation structure that your Hamiltonian gives in your system, then you cannot use this type of thermostats to calculate any of that, in fact. Yeah.
Okay. Thank you. Hopefully that answered the question. And another question from David is, can you comment on how you learn the polarizabilities?
Yes. So, so let's say, so this paper here, if you look at that, so what we used is here was a symmetry adapted Gaussian process regression model in which we took into account the symmetry of the polarizability tensor into the learning problem. So this is a Gaussian process regression, but the kernels that we use are different depending on the lambda order of the piece of the polarizability tensor that we want to predict. So there's the isotropic part that transforms like lambda equals 0, and the anisotropic part that is lambda equal 2 for the polarizability tensor. We have different kernels that keep these symmetry transformations in the SO3 space, and then what we do there is that simply we get a lot of structures for which we could calculate the polarizabilities or the periodic polarizabilities with FHI-aims, and we calculate the smooth overlap of atomic positions, so SOAP descriptors for all of that. That is what we use as inputs to build the kernels for the training set, and then we have the answer of the polarizability. We train the model by just doing the linear inversion of the GPR, and then we predict in a new structure by also representing it with SOAP descriptor.
Thank you, Mariana. So a question from the YouTube comments, so from Daniel Diesenbeck. Is it possible to perform thermodynamic calculations after performing the vibrational calculation? And do I need to ignore the translational and rotational modes, or does the program ignore them?
Can you read again the first part of the question?
So is it possible to perform thermodynamic calculations after performing the vibrational calculation?
I am not sure what is meant by thermodynamic calculations.
Maybe
in this context.
Free energy calculations. So
yes,
vibrational free energy.
Yeah. So yes. So this is something that I do believe, and I think James, you also know this. So the script that you will use tomorrow, it calculates the ZPE, right? But does it calculate the free energy too? I think not. No. So, so out of the top of my head, I don't remember whether we have any utility script that actually calculates vibrational free energies from anything. So the main message I would have to you here is that, yes, indeed, once you have the normal modes of vibrations and the normal frequencies in the harmonic approximation, this is all you need to calculate something like free energies, right, of the system. Whether that is shipped with the code or not, I don't know. And maybe tomorrow we can answer this question more. Personally, I have my own scripts, and in my group we have our own tool set of doing that. All we take as an input is a the normal modes of vibration and normal frequencies. And then whether you ignore or not in solids the first 3 vibrational modes, or in molecules the first 6, right? Because vibrational end rotations. That depends on the script. This is not done automatically inside FHI-aims.
Yeah, maybe I can just comment on this also. So the script that's used in the tutorial tomorrow, so the Python script doesn't compute these free energies, but we do have a Perl script in the code, which is referenced in the tutorial, but we actually use, which does calculate these, say, vibrational free energies. And it is our intention to put this into the Python script in the near future as well, and add additional.
Yes, and it could be that FHI-vibes does this also. I'm not so sure, but it could be, yes.
Okay, so more from the Zoom questions. So from Sandeep Kumar, what role does electron-phonon coupling play in the Raman spectra of superconducting or topologically interesting materials, and how can this be accurately modeled within the DFT framework and FHI-aims?
Not my area of expertise. I will not. So electron-phonon coupling can be calculated in FHI-aims. This is not the topic for today, but this is possible. So it's within the framework of DFPT. Electron-phonon coupling is well supported. There is actually also an entry of this roadmap that only talks about electron-phonon coupling. So if you were curious about the roadmap, it will also be there. So in that context, yes, it's possible to calculate electron-phonon coupling. What role it plays on the Raman spectrum of superconducting systems, not my expertise. I'm sorry, I cannot answer. I think it really depends on what superconducting system you're talking about and what type of superconductivity you have. But I don't know. And yes, I mean, but if what you're after is electron-phonon coupling matrix elements, yes, you can do. And maybe I would speak one more thing about something related, that FHI-aims is really great to simulate 2D materials, because you don't have to pay anything to put a vacuum in your system, because it's all localized basis. And so if you're looking at this new type of 2D materials and so on, and quantum materials in that realm, it's really great to do calculations of FHI-aims. You can do it very efficiently, and it's really nice.
Thanks, Mariana. So the next question from Raji asked about the link for the FHI-aims roadmap, and it's online. So maybe I can just quickly answer this by saying, yeah, Mariana said that it should hopefully be put on archive in complete in the next few weeks. We have pieces of it available at the moment, so one of my colleagues will type in the chat the links to the pieces that are available right now. And also, if you're interested in the full version at the moment, you can email us as well, and we'll send the email address that you can speak to as well. Okay, so next question from Aurélie Champagne. They have 2 questions. So in addition to vibrational spectra, Raman and IR, is it also possible to compute NMR spectra and/or absorption spectra? That's actually electronic absorption spectra.
Yes, NMR, yes. It's another incarnation of density function perturbation theory, but for magnetic fields, and that's also implemented. So yes, you can do that. I think yes, no, I'm sure there's also a roadmap entry on that one that I didn't cover. So it will also be in the roadmap. So NMR, yes. Optical absorption also, yes. So in the framework of TDDFT specifically, you can do that because we have TDDFT and even NFS dynamics now in the code. So linear optical absorption, yes, especially for molecules and also periodic systems. It's a little bit more. I mean, I have first-hand experience now because we're trying to use in the group. I think I would say the molecular part very good, very well developed, no problems. Periodic part is a bit slow still. It's robust but slow, but certainly about to be more developed. It's an effort in the group of Yasuke Kanai in North Carolina. So yes, so it's possible. Try it out. Also in the roadmap, it's explained how to do it.
Is electronic absorption also possible with BSE? Okay. And a second question from Aurelie, how does the code perform for metallic systems or systems with strongly correlated electrons?
So for metallic systems, the first question is metallic systems, right? Yes. Metallic systems very well. I mean, K-point handling is amazing. It's super parallelizable over K-points as well. So, no problems for metals and it all, yes. I mean, one thing that I don't know, I only talk about my own experience here in my group, together with my group, but converging the electronic structure, for example, of metallic slabs and so on is quite great and robust in FHI-aims in most cases. There are some pathological cases that will never convert, but in most cases, really, really good. It's different to some other cores that have a lot more difficulty converging things. So metals, really great. And then the other one was strongly correlated. Yes?
Yeah.
So there are there's a plus U implementation in the code that can handle more strongly correlated systems as well. You have to note that this is plus U in all electron, which is different to most plus U's that you will find in other codes that are not all electron normally in the literature. So the values of the U I hear, I don't work with that directly, so I'm just saying what I know of broad knowledge are quite different that you have to use, but this is also covered in one of the roadmap contributions.
I think we just have time for one more question, and we'll either answer the rest by typing, or you're invited to email us or Mariana if you have additional questions. So last question from Dimitri Ferha. Once the normal modes have been computed, how many additional calculations need to be done per normal mode to get the Raman spectra? Are these calculations more expensive compared to the numerical Hessian calculations?
Yes, maybe I just show here again quickly. Wait a second. So the overall answer to that question is yes. And I can tell you a bit more what you'll see in the tutorial tomorrow. So you have two ways to go about it if you like. Okay, so you can, for example, if you calculate the normal modes by finite differences here, right? You can, at the same time that you're calculating each one of the atomic displacements, you can also calculate, in this case, the dipole at each atomic displacement, or in this case, you can calculate the polarizability as well at each atomic displacement, okay? And if you calculate the dipole, for example, for non-periodic systems, this is not a huge overhead in the calculation. For the periodic system, it's a bit more of an overhead because you need to go through this Berry phase framework. So you have to calculate the Berry connection. This is done currently in reciprocal space, so it needs a little bit, for that part of the calculation, more K-points and so on. So you'll see tomorrow, it's a bit more costly. Here, at the same time that you calculate the atomic displacement, you have to calculate also the polarizability tensors. And this is a bit more costly, maybe it's like doing 3 more DFT calculations per step or so. I don't know, a factor 3 or 4, because you have to calculate this response of the density, and this is done through the FPT, for example, in this case. So this also adds a bit of cost. It depends on your system how much it is actually. And then you can build this Hessian matrix and diagonalize it all together. So then you get the normal modes, and you also get the matrix of transformation. So you know the change in alpha in the direction of the normal mode directly. Another way to go about it is that to calculate all the normal modes without calculating either mu or alpha at that point of the calculation. And then with those normal modes that you have, you just displace back and forth along that normal mode, and you calculate the dipole there, and then you get the same element. You can choose the way you want to do it, but you always will have to calculate on top of your typical normal mode calculation, either the dipole or the polarizability. That's it. And here also through a trajectory, at each time step, you also have to calculate the dipole or the polarizability. And so that's a little bit extra cost. I mean, a little bit, or maybe even 3 times more, something like that.
Great. Thanks, Mariana. So I think that will close the questions for this part. I'll just hand over back to Konstantin now before Alexandra's talk.